Swayam Prabha. Digital India. Educated India.
Okay. Good morning, everyone. So, we in the last class we have developed the theory of stability analysis using the bifurcation theory or linear stability analysis, and we have seen how to characterize, how to model a chemical engineering system by ordinary differential equation, and once we get that, by solving those set of equations you will be getting the steady states. Now, the stability of these individual steady states is a very it's a big problem in chemical engineering system. One has to run a particular system or process under a particular steady state, and that steady state has to be a stable steady state. Unless and until we do that, we cannot ensure the quality of the product that we are getting out of the whole process. Now, what we have done, we have developed the bifurcation theory, and also we have looked into the parameters, variation of the system parameters, and how that system parameters will lead to stable steady state to unstable steady state, and these points are known as the bifurcation points, where the steady state becomes a stable steady state becomes an unstable steady state because the parameters are changing their values. Now, we have identified two bifurcation point. One is the saddle node bifurcation point, another is the Hopf bifurcation points. In case of saddle node bifurcation points, the eigenvalues have to be real, and in case of Hopf bifurcation point, the eigenvalues will be complex conjugate. Now, if we summarize what are the various steps involving into these processes, first one will be, we will be getting the mathematical expressions to designate the particular system, and we solve the steady state part of those equations in order to get the steady state. In most of the chemical engineering processes, these equations will be leading to a set of algebraic equations, may be nonlinear. Then one has to invoke Newton-Raphson technique or some numerical iterative technique to solve this set of algebraic equations. So, solutions of these equations will be corresponding to the steady state of the system. Now, what we do? We take up each and individual steady state and evaluate and check their stability. So, the procedure for that is step number 2. The step number 2 will be first evaluating the Jacobian matrix, and the Jacobian matrix has to be evaluated at the steady state, at the concerned steady state, and then we will be looking into the eigenvalues and of this particular Jacobian matrix, and by looking into the sign of the eigenvalues, one has to identify that whether that steady state is stable or unstable. If eigenvalues are negative, they will be having a negative real part, then we will be getting a stable steady state. If the eigenvalues are complex conjugate with a negative real part, then the system becomes the steady state, concerned steady state is a stable steady state. If one of the eigenvalues is positive and all eigenvalues are negative, then again the system becomes unstable steady state. Now, one can also look into the change in parameters in the phase plane plot and can identify the bifurcation points at which the stable steady state, when these parameters will cross over the axis, imaginary axis, they will move, the steady state moves over on the right up plane and the real part becomes positive. So, this transition occurs at the bifurcation points, and there will be set of a particular relationship exists among all parameters where one can land up with the bifurcation point. So, that is very important and we have to avoid that. So, therefore, we can identify what are the bifurcation points, we can test the various steady state and their stability we can always examine. Now, if it is a two dimensional problem, then the problem becomes absolutely simple, and one will be getting the by looking into the trace value and determinant value of the Jacobian matrix, one can evaluate the stability of the steady state. For this particular case, for a two dimensional problem, the trace has to be negative and determinant has to be positive, then we will be getting a stable steady state. Now, for a multidimensional problem, one has to use the Routh-Hurwitz criteria to determine the conditions, to evaluate the conditions of stability of the steady state we are concerning. So, we are in the last class we have developed a full theory of linear stability analysis or the bifurcation theory, and then we took up some of the examples, and several examples we have taken up, and in the last example what we are solving, it was half done. We will be completing that problem, look into one more problem and then move over to the partial differential equations in continuous domain. So, if you remember, the example problem we were looking into is that the system is designated by these two ordinary differential equations, dx dt is equal to x a y minus 1 plus b, that is equal to f, and dy dt is y into 5 minus b x plus y, that will be equal to g. Now, we have already solved this problem in the last class. There are three steady state available in this problem. The first steady state S1 is 0 0, the steady state number 2 S2 is 0 minus 5, and steady state 3 S3 is given by 5 a minus b plus 1 divided by a b and 1 minus b over a. So, we have already checked the stability of the first two steady state. The first steady state 0 0 was unconditionally unstable. We have evaluated that. Unstable, and this will be stable if the following conditions will hold good. If a is greater than b minus 1 divided by 5 and 5 a is greater than b minus 6, then this is the condition, these two are identical conditions. Okay, so this will be more stringent condition. So, subject to this, one has to get a stable steady state. Now, in today's class, what we will be doing, we will be examining the steady state number 3. So, let us start with that. The steady state S3 is given by 5 a minus b plus 1 divided by a b and 1 minus b divided by a. This is the steady state x value, this is the steady state y value. So, we evaluate the Jacobian matrix at this particular steady state values. So, this becomes 0, 5 a minus b plus 1 divided by b, and this will be b into b minus 1 divided by a and 1 minus b divided by a. So, now if you look into the trace of a, that has to be less than 0. So, therefore, b is greater than. So, if trace is less than 1 less than 0, that means the two diagonal elements have to be added up. So, it will be 1 minus b divided by a should be less than 0, therefore, b is greater than 1. And the other condition is determinant of a is greater than 0. So, therefore, minus this into this is 0. So, minus of this. So, minus b into b minus 1 divided by a into 5 a minus b plus 1 divided by b, that has to be greater than 0. So, this b will cancelling out, a will be going to 0. So, it will be b minus 1, then b minus 5a or we can put it like this, b minus 5a minus b plus 1 should be. So, there is a minus sign, but this should be less than 0. So, this condition can be satisfied, but we have already seen that for a stable steady state, trace must be equal to 0, that means b must be greater than 1. That means in order to, so this is always positive. Now, to get a negative number, it has to be negative, then only the product will be negative. So, therefore, in order to get the stability, we must have minus b plus 5a plus 1 should be less than 0. So, b should be greater than 5a plus 1. So, if these two conditions are satisfied simultaneously, b is greater than 1 and b is greater than 5a plus 1, and a is always if you remember, a is always positive and it is a non-zero positive parameter. So, therefore, therefore, b is greater than 5a plus 1 will be always satisfied. So, using these two conditions, b has to be positive and it has to be greater than 1, and secondly it has to be greater than 5a plus 1. So, if these two conditions are satisfied, then the steady state S3 is stable and we will be getting a very stable steady state. Now, we will be looking into the next problem. The next, so that completes this problem, then we will go to the next problem. Next problem is the chemical engineering system is characterized by two ordinary differential equations. These are dx1 dt is equal to f is equal to x1 square minus a x1 x2 minus x1, and dx2 dt is equal to g is equal to b x2 square plus x1 x2 minus 2 x2. So, we can, and these a b are the parameters and these parameters are positive parameters in the system. So, one can get the various steady states and check into the solution of the steady state. Now, first step will be evaluation of steady state. Steady state. So, we put dx1 dt equal to 0 and dx2 dt equal to 0. So, what we will be getting from the first equation is x1 square minus a x1 x2 minus x1 should be equal to 0. So, take x1 common. So, it will be x1 minus a x2 minus 1 is equal to 0. So, that is equation number 1. So, we will be getting either x1 equal to 0 and x1 is equal to a x2 plus 1. Now, from the equation number 2, we will be getting b x2 square plus x1 x2 minus 2 x2 is equal to 0. So, therefore, you can take x2 as common, b x2 plus x1 minus 2 is equal to 0. So, therefore, from this we will be getting x2 equal to 0 and x1 is equal to 2 minus b x2. So, we will be getting two steady state, one is x1 equal to 0, another is x2 equal to 0. So, we can identify the steady state 1 as x1 equal to 0, x2 is equal to 0. Now, one can solve these two equations simultaneously and can get the second steady state. If we really solve them, it will become a x2 plus 1 is equal to 2 minus b x2. So, we can take x 2 common, change over the sides, this becomes a plus b and it will be 2 minus 1 is 1. So, x 2 will be 1 over a plus b, and what is x 1? X 1, if you remember, this becomes 2 minus b x 2. So, b divided by a plus b. So, it becomes 2 a plus 2 b minus b divided by a plus b. So, this will be 2 a plus b divided by a plus b. So, that will be second steady state. So, steady state 2 will be first. So, this will be 1 over x is equal to 2 a plus b. So, it will be 2 a plus b divided by a plus b, and x 2 is 1 over a plus b. So, this is steady state number 2. The first steady state we have already seen 0 0 is the first steady state. Then if you check that x 1 is equal to 0, x 1 is equal to 0 and x 2 is equal to 2 by b, is another steady state, because if you look into this equation, x 2 is equal x 1 is equal to 2 minus x 1 is equal to 2 minus b x 2. So, putting x 1 equal to 0, you will be getting another solution 2 by b. So, steady state number 3 will be 0 and 2 by b. So, this will be the third steady state. Similarly, you can get another steady state, that is steady state number 4. Steady state number 4 will be x 2 equal to 0. So, if x 2 equal to 0, if you look into the expression of f, if x 2 is equal to 0, and you will be getting g will be satisfied, and if x 2 equal to 0, then you will be getting x 1 is equal to 1. So, if you look into the equations dx 1 dt equal to 0 and dx 2 dt equal to 0, you will be seeing that x 2 is equal to 0 and x 1 is equal to 1 will give another steady state. They will satisfy both steady state equation. So, SS 4, the steady state number 4 is given by 1 0. So, we can identify that there are 4 steady state in this particular problem. Then we will take up each and individual steady state and check their stability. So, next we will do, so we have identified the steady state. Next what we will do, we will be evaluating the Jacobian matrix and evaluate each and every for each and every steady state we will evaluate the Jacobian matrix. Next we evaluate the Jacobian matrix, that will be nothing but partial derivative of f with respect to x 1, del f partial derivative of f with respect to x 2, partial derivative of g with respect to x 1, partial derivative of g with respect to x 2. So, that is the Jacobian matrix. If we evaluate all these partial derivatives and put them into here in the elements of the matrix, this becomes 2 x 1 minus a x 2 minus 1 minus a x 1 x 2 2 b x 2 plus x 1 minus 2. So, this is the Jacobian matrix. Now we take up individual steady state and check their stability. First steady state we talk about is 0 0. So, j becomes minus 1 0 0 and minus 2. We evaluate the j minus lambda I, the eigenvalues. So, it becomes minus 1 minus lambda 0 0 minus 2 minus lambda. So, we evaluate the eigenvalues, the put determinant of j minus lambda I is equal to 0. So, therefore, we will be getting lambda 1 is equal to minus 1 and lambda 2 is equal to minus 2. So, this steady state is unconditionally stable. 0 0 is always stable. You can interpret this from the determinant value and trace value, trace turns out to be negative, which has to be the case, and determinant turns out to be positive. So, therefore, this steady state SS1 is unconditionally stable. Next, we check the second steady state. So, we take up steady state number 4, because it has only value 1 and 0, that is the steady state value. So, evaluate the Jacobian matrix. The Jacobian matrix becomes 2 minus 1 minus a 0 and minus 1. So, this becomes 1 minus a 0 and minus 1. So, if you look into determinant of j minus lambda I is equal to 0, if you put that, then what we will be getting is that 1 minus lambda minus 1 minus lambda minus 0 into this, so there should be equal to 0. So, 1 minus lambda and 1 plus lambda is equal to 0. So, you will be having two roots of this equation. So, lambda 1 will be 1 and lambda 2 will be minus 1. Since one of the root is positive, then 1 4 steady state 4 is always unstable and unconditionally unstable, we can say it. Okay. Next, we check the third steady state. The next steady state will be 0 and steady state number 3. So, it will be 0 and 2 by b, and this will be given by the now we evaluate the Jacobian matrix at these values. So, it will be minus 2b by a minus 2a by b minus 1 0 2 by b, then 2b into 2 by b plus 0 minus 2. So, this becomes minus 2a by b minus 1 0 2 by b and 2. Okay. So, 4 minus 2 is will be plus 2. So, we will be getting the determinant of j minus lambda I should be equal to 0. So, if you do that, what we will be getting is that 2 minus lambda into minus 2a by b minus 1 minus lambda is equal to 0. So, lambda 1 will be 2 and lambda 2 will be 1. So, lambda 2 will be it will be 2a minus b minus 1 minus lambda. So, lambda 2 will be 1 minus will be common 1 plus 2a by b, but since you will be having one eigenvalue. So, there will be a minus sign here. So, this will be positive. So, it will be lambda 2 will be negative, but lambda 1 is positive. So, therefore, steady state 3 will be unconditionally unstable. Is steady state 3 is always unstable. So, likewise, we can evaluate the steady state 4 as well. The steady state 4 becomes the complicated one. So, SS 4 is 2a plus b divided by a plus b and 1 over a plus b. So, therefore, we evaluate the Jacobian matrix at this. So, this becomes 2 into 2a plus b divided by a plus b minus a divided by a plus b minus 1 minus a into 2a plus b divided by a plus b 1 over a plus b, then this becomes 2b by a plus b plus 2a plus b divided by a plus b minus 2. We simplify all this and I am just writing the final expression of Jacobian matrix. This becomes 2a plus b divided by a plus b and 1 over a plus b, that is 1 minus a into 2a plus b divided by a plus b, and this will be b divided by a plus b. So, if you look into the, do not worry about anything else, if you look into the trace of this Jacobian matrix, this becomes 2 a plus b divided by a plus b plus b into a plus divided by a plus b. So, it becomes 2. So, trace is 2, which is greater than 0. So, steady state 4 is always unstable. So, therefore, this way we can evaluate the that completes this problem, and this problem demonstrates how the various steady states of a particular problem can be evaluated, can be checked for its stability, and also we can look into the combination of the parameters for which the system becomes stable or the steady state becomes stable or unstable. So, we finished the stability analysis by bifurcation theory or linear stability analysis for any chemical engineering system. For a 3 into 3 matrix or 3 into 3 variables or multi-dimensional problem, one can take recourse to the Routh-Hurwitz criteria or Routh table to evaluate the conditions on the steady states, the stability of the steady state. Next, we move forward and we will move towards the differential equations, and first we will talk about some of the basic definitions of the differential equations, and we will be mostly talking about partial differential equations. And it is understood that most of you have already done lots of solutions for the ordinary differential equations in your undergraduate study, and we will be looking into the solution of the partial differential equations. First, we will characterize the partial differential equations, we will be looking into various properties of partial differential equations, we will characterize them, and then we will be looking into the solution techniques. We will be not only equations, we will be talking about the boundary conditions, we will classify the boundary conditions and see how these boundary conditions will be appearing for different physical situations under chemical engineering applications, and then we will be looking into the solutions. We will be taking recourse to some of the techniques. One is the separation of variable techniques, then similarity solution, then we will be looking into the Laplace transform, we will be looking into the Fourier's transform, then we will see the general method of solution for non-homogeneous partial differential equation using Green's function. So, let us, with that preamble, we will start the portion of partial differential equation. Okay. So, partial differential equations are basically equations which will be having more than one independent variable. If your system or equation have more than one independent variable, then it is called a partial differential equation. Next, we talk about the order of PDE. Ordered is the highest derivative appearing in the equation. Appearing in the equation. For example, this equation del u del t is equal to del square u del x square. In this PDE, the highest derivative occurring is second order. So, the order is 2. Next, del u del t is equal to del u del x plus del square u del x square plus del u del y. Since the highest derivative occurring is the second order, so again this is having order 2. For example, del u del t is equal to del u del x plus del cube u del x square del y, then the highest derivative that is appearing is 3. So, it has an order of 3. So, the highest derivative that is appearing in the partial differential equation is defined as its order. Then we will discuss about the linearity and nonlinearity of the partial differential equations. So, first we talk about the linear partial differential equation. We call that partial differential equation as linear if u del x del u del y and higher order derivatives occur at most in first power and no product terms exist are present between these. Then we call these partial differential equations as linear. That means power means del u del x raised to the power 1. If that is the case, then this is linear partial differential equation. Similarly, if we have a term del u del y square, then it is not linear. Similarly, if we have a term del square, if we have a term del square u del x square, this is having order 1, but power 1. Del square u del x square square. So, this will be having this order, the del square u del x square is order 2, but power 1. In this case, this will be order 2, but power 2. Order is also 2. So, this is linear, this is non-linear. If any product term is present like u del x, then it is non-linear. If any product term is present like del u del square u del x square, u del u del x square or u del square u del x del y or del u del x del u del y, again they are non-linear. So, whenever the product terms are absent, whenever the power is 1, then the partial differential equation is termed as linear partial differential equation. We will take up some of the examples. Del u del t is equal to del square u del x square. It has order 2, but a power 1, and there is no product term present. So, this is a linear PDE. U del t is equal to del square u del x square. Again, here the product term is present between the dependent variable and its derivative, and the order 2. So, therefore, this is nonlinear because of the product term present. Third one is del u del t is equal to u del square u del x square. Again, this is order 2, but the product term is present u del square u del x square. So, therefore, again this is nonlinear. del u del t square is equal to del square u del x square. So, again the power is 2 of this, although the order is 2, but this is again, since the power is not 1. So, it is non-linear. So, the important is the power should be 1 and no product of dependent variable and its derivative. If that is the case, we call that partial differential equation as linear partial differential equation. Okay. Next, we talk about the homogeneous partial differential equation. In case of homogeneous, if every term contains independent variable or its derivative, then it is called homogeneous. Then the equation homogeneous. That means, every term of the equation must be the dependent must be containing depending variable or its derivative. If at least one term does not contain dependent variable or its derivative, then this is non-homogeneous PDE. So, I will take up some example. Del u del t is equal to del square u del x square, some constant k. Now, in this equation, this term constant k does not contain the dependent variable u or its derivative. So, because of this equation becomes non-homogeneous. Del u del t is equal to del square u del x square plus sin x. Now, this term contains the independent variable, but this term does not contain the dependent variable. So, again, this is again a non-homogeneous equation. On the other hand, just look into this example. Del u del t is equal to del square u del x square plus u sin x. In this equation, all the term contains the dependent variable u and its derivative contains u. So, again this is homogeneous. Okay. So, these are the various types of general types of equations we are talking about. Then we will look into the boundaries. Equations, partial differential equations cannot be solved without the boundaries. Now, there are two types of boundaries generally we consider. One is the closed boundary, another is the open boundary. What are closed boundaries? The closed boundaries are a boundary is term is closed boundary is closed if it is completely surrounded the region of interest and boundary conditions are specified everywhere on that boundary. So, that particular boundary is called as the closed boundary, even if a part of boundary goes to infinity and we specify boundary condition at infinity, it is a closed boundary. If a boundary condition is specified at infinity, if that is specified, then it cannot be an open boundary, it will be a closed boundary in that case as well. Next, we look into an open boundary. What is defined as an open boundary? The open boundary is defined as when a part of the boundary goes to infinity, but we do not impose any condition on that. Then the boundary is called the open boundary. Okay. So, I will give an example for this particular problem. Let us say del u del t is equal to del square u del x square. Now, in this case x at x is equal to 0, u is equal to 0, at x is equal to infinity, and let us say at x equal to 0 u is equal to u naught, at x is equal to infinity u is equal to 0. Now, although this boundary is situated at infinity, but since this condition is specified, this is a case of closed boundary condition. On the other hand, if you look into the other boundary of the t, that is open and that goes to infinity, but we cannot impose any condition on that t. So, therefore, the boundary conditions on t at infinity is not is an open boundary condition. Next, we look into the several types of boundary conditions, classifications of boundary conditions. First boundary condition is Dirichlet boundary condition. Now, in this case, whenever the value of dependent variable is specified, whenever the value of dependent variable is specified at any boundary, then this boundary condition is called Dirichlet boundary condition. For example, at y is equal to 0, t is equal to t naught. This is an example of Dirichlet boundary condition. At y is equal to 0, u is equal to 0. So, this is an example of Dirichlet boundary condition, where the value of the dependent variable is specified, whether it is 0 or some specified value. So, then we call this boundary condition is Dirichlet boundary condition. Next we talk about next boundary condition is Neumann boundary condition. Neumann boundary condition is whenever a derivative of dependent variable is specified on a boundary, we call that boundary as Neumann boundary condition. That means, a physical example in chemical engineering system is an insulated wall. An insulated wall means at a boundary on some surface S, you have minus k del t del y will be is equal to on a surface S will be minus k del t del s. Okay, is equal to 0, where s is the normal direction on that surface. So, therefore, the derivative is defined on, so k is being constant, or it even if it is not constant does not matter, it becomes del t del s equal to 0. So, this is the derivative of the dependent variable is specified on this boundary. So, this is a Neumann boundary condition. For example, another example is the boundary condition on velocity at liquid water liquid air interface, let us say air water interface. In that case, we write del u in the liquid, del y is equal to 0 at interface. This comes because of the matching of the shear stress at the interface, but the viscosity values. So, this velocity gradient will be multiplied by the viscosity to get the shear stress, but the viscosity in the air is 2 order of magnitude less compared to that of water. So, that will be we can approximate, we can neglect that part, and we can approximate del u L in the liquid, del y is equal to 0. So, again the derivative of the dependent variable is specified at this boundary. So, therefore, this boundary condition is a Neumann boundary condition. Okay. Next one is Robin mixed boundary condition. In this case, at any boundary, the condition is given by an algebraic expression between dependent variable and its derivative. Whenever a dependent variable and its derivative both are connected by a simple algebraic equation, and that is the condition that is specified at the boundary, then we call that boundary as a Robin mixed boundary condition. So, it is basically mixture of Neumann boundary condition and Dirichlet boundary condition. For example, a surface, we talk about a heat surface, a fin maybe, and that the edge of the fin is exposed to air. Air is having a temperature T infinity, and at that particular point, the at the particular boundary, let us say at x is equal to L, the temperature is T and H is the heat transfer coefficient. Then the other steady state, whatever the heat that has come by conduction is taken away by the convection of the air. So, minus k at the boundary at let us say x is equal to L, minus k del T del x, that is the heat that has appeared at this boundary by conduction should be taken away by convection of air, that is ambient air. So, H into T minus T infinity, H is the heat transfer coefficient. So, therefore, this boundary condition is a mixture of dependent variable T and its derivative del T del x, and it is given by an algebraic equation. So, this is an example of Robin mixed boundary condition. Now, in this the case like del T del x is equal to 0, it is a Neumann boundary condition. This is a homogeneous boundary condition. Similarly, if you have del T del x is equal minus k del T del x is q, then because of this term this becomes a non-homogeneous boundary condition. So, this becomes a homogeneous boundary condition and this becomes a non-homogeneous boundary condition. That means, even in the boundary condition, if there is any term present which does not contain the dependent variable, then we call that equation as homogeneous boundary condition. For example, in this equation there is one term, there is at least there is no term that is present which contains the which does not contain the dependent variable or its derivative. So, this is a homogeneous boundary condition. On the other hand, in this equation there is at least one term is present which does not contain the dependent variable and its derivative. So, this is a non-homogeneous boundary condition. Now, in this equation there are three terms, two terms on the right hand side, one term on the left hand side. The first term on the left hand side, it contains a derivative of the term on the left hand side contains a derivative of the dependent variable t. The first term on the right hand side, it contains the dependent variable t h times t, and the second term on the right hand side, it contains a constant term h into t infinity, which does not contain the dependent variable. So, this term does not contain dependent variable. So, therefore, this is a non-homogeneous term and this boundary condition is a non-homogeneous boundary condition. On the other hand, if we can we can make the non-homogeneous boundary condition, we can make it homogeneous, minus k del T del x is equal to h T minus T infinity. So, this is a non-homogeneous boundary condition. This is the non-homogeneous term. If we now define a theta such that theta equal to T minus T infinity, then this equation, this boundary condition becomes k del theta del x is equal to h into theta. But in this particular form of the equation, there is no term present which is not a function or which is not a function of theta or its derivative. Now, all the terms, there are two terms present in this equation, both the terms contains either the dependent variable theta or its derivative. So, therefore, this equation becomes a homogeneous boundary condition. So, we can convert the non-homogeneous boundary condition into homogeneous boundary condition by defining an appropriate term. Okay. So, I stop here at this point. We take up some more characteristics of the partial differential equations in the next class. Thank you very much.